Have you ever wondered how a spacecraft that is already in orbit, moving at several kilometers per second along a path determined by gravity and momentum, manages to change where it is going without the benefit of roads, steering wheels, or the kind of direct mechanical control that makes navigating on Earth feel intuitive? The question seems simple until you realize that the answer requires confronting one of the most counterintuitive aspects of orbital mechanics. In orbit, the relationship between where you point your engines, how long you fire them, and where you end up is almost exactly the opposite of what everyday experience would suggest. Speeding up does not simply make you go faster along your current path. It changes the shape of your path in ways that carry you to completely different places. Slowing down does not simply reduce your speed. It drops you into a lower orbit where paradoxically you end up moving faster. And turning, in the aeronautical sense of pointing your vehicle in a different direction, accomplishes almost nothing useful in orbital mechanics unless it is accompanied by a precisely timed engine burn. Understanding how spacecraft navigate in orbit requires abandoning the intuitions built from driving, flying, and sailing, and replacing them with a way of thinking about motion that Newton formulated and that Kepler described empirically before Newton explained why. A way of thinking that feels alien at first, but that becomes, with enough exposure, one of the most elegant frameworks for understanding motion that physics has produced. The foundation of all orbital trajectory adjustment is the concept of the delta V, which is the change in velocity that a spacecraft applies to alter its orbit. Delta V is measured in meters per second and represents not just a change in speed, but a change in the velocity vector, meaning it has both a magnitude and a direction. When a spacecraft fires its engines, it applies a delta V in a specific direction for a specific duration, and the result is a new velocity vector that places the spacecraft on a different orbit than the one it was following before the burn. The relationship between the direction of the delta V and the resulting change in orbit is what makes orbital navigation so counterintuitive. A delta V applied in the direction of motion, called a prograde burn, increases the spacecraft's orbital energy and raises the opposite side of its orbit. A delta V applied against the direction of motion, called a retrograde burn, decreases orbital energy and lowers the opposite side of the orbit. A delta V applied perpendicular to the orbital plane, called a normal burn, changes the inclination of the orbit without significantly affecting its size or shape. And a delta V applied radially, either toward or away from the body being orbited, changes the shape of the orbit in more complex ways that are generally less efficient than prograde or retrograde burns for most practical maneuvers. The prograde burn is the most commonly used maneuver in orbital mechanics, and its effects illustrate perfectly why orbital navigation requires such a different mental model from terrestrial navigation. When a spacecraft in a circular orbit fires its engines in the prograde direction, increasing its speed, the immediate effect is that the spacecraft is now moving faster than the orbital velocity required for a circular orbit at that altitude. This means that gravity is no longer strong enough to keep the spacecraft in its current circular orbit, and the spacecraft begins to move outward, climbing to higher altitudes. But as it climbs, it loses kinetic energy and gains potential energy, slowing down as it rises. The orbit is no longer circular but elliptical, with the burn point as the lowest point of the ellipse, called the periapsis, and the highest point of the ellipse, the apopsis, on the opposite side of the orbit. The spacecraft continues along this ellipse, rising to the apopsis, where it is moving at its slowest, and then falling back toward the periapsis, where it is moving at its fastest. This is the Keplerian orbit that results from a single prograde burn from a circular starting orbit, and it is the building block from which more complex maneuvers are constructed. The Hohmann transfer, which uses two prograde burns to move a spacecraft from one circular orbit to another circular orbit at a different altitude, is the most fuel-efficient two-burn transfer between circular orbits, and illustrates how spacecraft planners think about trajectory adjustment as a sequence of precisely timed burns rather than a continuous steering process. The first burn raises the apoapsis of the orbit to the altitude of the destination orbit, placing the spacecraft on a transfer ellipse. The spacecraft then coasts along this transfer ellipse, consuming no propellant until it reaches the apoapsis. At the apoapsis, a second prograde burn circularizes the orbit at the new altitude, adding the velocity needed to match the circular orbital velocity at that altitude. The two-burn structure of the Hohmann transfer reflects a deep efficiency principle. Each burn is performed at a point in the orbit where the Oberth effect ensures maximum energy gain per unit of propellant consumed, which for prograde burns is always at the point of lowest altitude and highest velocity in the orbit. Performing the same total velocity change at any other point in the orbit would result in a less efficient use of propellant and would not achieve the desired final orbit with the same precision. The bi-elliptic transfer is a three-burn maneuver that is more fuel-efficient than the Hohmann transfer for very large changes in orbital altitude, a counterintuitive result that surprises many people when they first encounter it. The bi-elliptic transfer performs a first burn to raise the apoapsis to an altitude much higher than the destination orbit, a second burn at that high apoapsis to raise the periapsis to the destination altitude, and a third burn to circularize the orbit at the destination altitude. The total delta V required for this three-burn sequence is lower than the two-burn Hohmann transfer when the ratio between the destination orbit radius and the starting orbit radius exceeds approximately 11.94. The reason is that the Oberth effect benefits the burns more when they are performed at higher speeds near the periapsis of highly elliptical orbits, and the bi-elliptic transfer structure allows both the first and third burns to be performed at very high speeds near the periapsis. The cost of this efficiency is time. The bi-elliptic transfer takes much longer to complete than the Hohmann transfer because the spacecraft has to coast along two highly elliptical orbits rather than one. And for the most extreme cases, the additional time required can be weeks or months. Orbital plane changes, which alter the inclination of the spacecraft's orbit relative to the equatorial plane or some other reference plane, are among the most propellant-expensive maneuvers in orbital mechanics and illustrate why the geometry of launch trajectories is so carefully chosen to minimize the need for plane changes in space. To change the inclination of an orbit, a spacecraft has to apply a delta V perpendicular to the orbital plane, and the amount of delta V required depends on both the desired inclination change and the current orbital velocity. At low Earth orbit, where orbital velocities are approximately 7 to 8 kilometers per second, changing the orbital inclination by 90 degrees requires a delta V of approximately 10 kilometers per second, which is more than the total delta V needed to reach low Earth orbit from the ground in the first place. This is why launching into the correct inclination from the ground is so much more efficient than launching into a convenient inclination and correcting it later in space. The most efficient way to perform a plane change is to combine it with an altitude change, performing the plane change at the highest point of a transfer ellipse where the orbital velocity is lowest, and therefore the delta V required for the inclination change is smallest. The rendezvous problem, which is the challenge of bringing a spacecraft from one orbit into proximity with another spacecraft in a different orbit, is one of the most complex and operationally demanding trajectory adjustment problems in human spaceflight. The fundamental difficulty is that two spacecraft in different orbits are not simply at different positions in space. They are in different states of motion that are completely determined by their respective orbits. And the only way to bring them together is to change one of the orbits so that it intersects the other at a time when both spacecraft are at the intersection point simultaneously. This requires precise knowledge of both orbits, careful calculation of the required maneuver sequence, and execution of the burns with sufficient accuracy that the resulting trajectory brings the spacecraft to within a few hundred meters of the target, close enough for proximity operations to begin. The Apollo program's lunar orbit rendezvous, where the lunar module had to ascend from the lunar surface and rendezvous with the command module in orbit around the moon, demonstrated that this problem could be solved reliably with the computing resources available in the 1960s. Today, the automated rendezvous systems used by cargo spacecraft approaching the International Space Station solve the same problem with greater precision and completely autonomously, without any human input during the final approach phase. The phasing maneuver is a specific type of orbital adjustment used to change the timing of a spacecraft's arrival at a particular point in its orbit relative to a target that is ahead of or behind it in the same orbit. If two spacecraft are in identical orbits but separated in phase, meaning one is ahead of the other in the orbit, the trailing spacecraft cannot simply fire its engines to accelerate and catch up, because a prograde burn would raise the apopsis of its orbit and carry it to a higher orbit where it would actually move more slowly and fall further behind relative to the leading spacecraft. To catch up with the leading spacecraft in the same orbit, the chasing spacecraft has to lower its orbit, which increases its orbital period and causes it to move faster through a shorter orbital path, eventually lapping the target. The maneuver sequence is a retrograde burn to lower the orbit, followed by a coast phase during which the spacecraft gains phase angle relative to the target, followed by a prograde burn to raise the orbit back to the target orbit altitude at the moment the two spacecraft are at the same orbital location. Calculating exactly how much to lower the orbit and how long to coast requires precise knowledge of the relative positions and velocities of both spacecraft and careful numerical integration of the orbital equations. The gravity assist maneuver, which uses the gravitational field of a planet or moon to change both the speed and direction of a spacecraft's trajectory without consuming propellant, is another form of trajectory adjustment that has been used to enable missions that would have been impossible with chemical propulsion alone. When a spacecraft approaches a planet, the planet's gravity pulls it toward the planet, accelerating it as it approaches and decelerating it as it moves away. If the spacecraft's trajectory is carefully designed so that the hyperbolic path it follows as it swings around the planet is oriented in the right direction relative to the planet's orbital velocity around the Sun, the spacecraft can exit the planetary encounter with a significantly different velocity relative to the Sun than it had on arrival. The change in velocity relative to the Sun comes not from the spacecraft's engines, but from the transfer of momentum from the planet to the spacecraft. And because planets are so much more massive than any spacecraft, the change in the planet's own orbital velocity due to this momentum transfer is completely negligible. The Voyager missions, the Galileo mission to Jupiter, the Cassini mission to Saturn, and the New Horizons mission to Pluto all used multiple gravity assists to reach their destinations with velocities that would have required vastly more propellant to achieve through direct propulsive burns. The continuous low-thrust trajectory adjustment performed by ion propulsion systems represents a fundamentally different approach to orbital navigation than the impulsive burns performed by chemical engines. An ion engine produces thrust that is orders of magnitude smaller than a chemical engine, but can sustain that thrust for months or years at a time, gradually accumulating a total velocity change that far exceeds what a chemical engine could achieve with the same mass of propellant. The trajectory adjustment performed by an ion-propelled spacecraft is not a series of discrete maneuvers separated by coasting phases, but a continuous spiral that gradually evolves the spacecraft's orbit over weeks and months. Planning and executing this continuous spiral trajectory requires mathematical techniques that are quite different from the impulsive burn calculations used for chemical propulsion maneuvers. And the resulting trajectories often look nothing like the elliptical transfer orbits that chemical propulsion produces. The Dawn spacecraft, which used ion propulsion to travel from Earth to the asteroid Vesta and then from Vesta to the dwarf planet Ceres, followed continuous spiral trajectories between its destinations that would have been completely impractical to describe as sequences of impulsive burns, and that required dedicated trajectory optimization software to plan and execute. The autonomous navigation capability of modern spacecraft has transformed the operational reality of trajectory adjustment from a ground-controlled process that required hours or days of ground team involvement for each maneuver to a capability that some spacecraft can execute entirely on their own based on onboard sensor measurements and navigation algorithms. The optical navigation system used by the OSIRIS-REx spacecraft during its approach to the asteroid, Bennu measured the position of Bennu relative to background stars using the spacecraft's own cameras, computed its own trajectory relative to Bennu using this optical data, and autonomously planned and executed the small trajectory corrections needed to bring it to within a few hundred meters of the asteroid's surface for sample collection. This level of autonomous navigation capability is essential for missions to small bodies far from Earth, where the round-trip communication time can be tens of minutes, and the precision of maneuver timing required for proximity operations cannot be achieved through ground-commanded maneuvers alone. What the complete picture of orbital trajectory adjustment reveals is that navigating in space is not a matter of pointing and flying, but a matter of understanding how energy is distributed between kinetic and potential forms in a gravitational field and manipulating that distribution through precisely timed applications of force in precisely chosen directions. Every maneuver a spacecraft performs changes not just its current position and velocity, but the entire future trajectory it will follow. And the art of orbital navigation consists of choosing maneuvers that change the trajectory in exactly the desired way while consuming the minimum possible amount of the propellant that is always, in every mission, the scarcest and most valuable resource aboard. It is a form of engineering that operates on timescales of hours, days, and months, in an environment where mistakes cannot be corrected by simply applying more force, and where the most elegant solution is almost never the most obvious one. And in that gap between the obvious and the elegant lies the entire discipline of orbital mechanics, one of the most beautiful applications of Newtonian physics that human ambition has ever demanded.